All right, so looking at our schedule, we're going to be continuing our discussion about substitution today. Project 2 is due, so please put Project 2 in your folder before you leave. And Project 3 has been assigned. I passed it out. There are copies on your tables. Project 3 is due February 24th. So upcoming things, we've got Quiz 3 coming up, Project 3 coming up, and Test 1 coming up. Okay, so today we're going to learn how to use the substitution technique on definite integrals, meaning where we have limits of integration, okay, as opposed to just finding an antiderivative. Okay, and then we're also going to see how to do some weird or tricky substitutions. So there are two ways to evaluate a definite integral by U substitution. I'm going to do both of them. One of them is technically incorrect, and if you write it this way, you will lose a little bit of credit. Okay. So I'm going to write it all out, and then you can tell me what's wrong with it. So if I were going to do U substitution on this integral, I start by looking at the integrand, and I say, is there a function in there whose derivative or something close to its derivative also appears in the integrand? X squared plus 1 is a really good choice for a U. It's an inside of a composition, okay, so that's typically a good choice for you, a function that's inside. And the derivative of x squared plus 1 is 2x, and an x also shows up in our integrand. So we have a good chance that the x's will cancel. So let's go ahead and use that as my U. Okay, so I'm going to let U be x squared plus 1, which means du dx is 2x, which means if you treat du dx like a fraction and solve for dx, you get dx is du over 2x. All right, so now I'm going to go ahead and make all my substitutions. So this becomes the integral from 0 to 2 of x. That's not an obvious substitution. X squared plus 1 is being substituted with a u, and dx is get substituted with a du over 2x. So that was a good choice of u because the x's now cancel. That 2 that showed up, that I have introduced a constant of 2, it's in the denominator of a fraction, right? So when I pull it out of the integral, it becomes 1/2. That has to stay in the denominator. So that's a really common mistake, is that when people pull that out, they write it as a 2. It's a 1/2 because it's in the denominator. And then this becomes 0 to 2 of u cubed du. Okay. Now, another common mistake is that at this point, people try to substitute back in, right? What should I do before I substitute back in? Take the antiderivative. Yes, that's the whole idea, is to create a function that's easier to take an antiderivative of. So I've got 1/2. The antiderivative of u cubed is going to be u to the 4th over 4. And I'm going to evaluate all of that from 0 to 2. Okay. Now I can substitute in my value, my expression for u. Okay, so this becomes, u is actually x squared plus 1. So I have x squared plus 1 raised to the 4th power all over 8. And I'm going to evaluate that from 0 to 2. Everybody okay with that so far? Okay, so now when I plug in a 2, did I do this? I did, yeah. It comes out to 78. Well, let's write it out, because I'll have my calculator do some of the dirty work here. Okay, so I tend to let my calculator do a lot of my arithmetic. So my function that I'm trying to evaluate, that I want to plug a 2 into and a 0 into, I can just type it into y1. So I'm going to put x squared plus 1 raised to the 4th all over 8. And then I can use my table to tell me the value at 2 and at 0. So I get 78.125. When you plug in a 2, you get 0.125 when you plug in 0. So that comes out to 78. All right, let's have the calculator check if 78 is actually the answer. Because I can have my calculator evaluate this integral straight away, numerically. Okay. So I'm going to go back to y equals. I'm going to put in the original integrand. So I have x times x squared plus 1 cubed. So I would like to know the area under that curve from 0 to 2. My calculator can do that. Just go to my home screen. I'm going to go math, function integrator. I want to integrate y1 with respect to x from 0 to 2. And I get 78. Okay, so it looks, I got the right answer by using the fundamental theorem of calculus and a U substitution. Okay, so if I got the right answer, why is this the incorrect method? What's wrong here? That's a good idea, but it's not that. Yeah. Oh, yeah, so I changed notation. Yeah, no, that's not the problem. Right. This is the same, that means the same thing as that. Yeah. It does have to do with the limits of integration though. 0 and 2. What kind of values are those? Are they x values or u values? Those are x values, right? They're on the original question. 0 and 2 are x values because this is x is the variable that's showing up in my original problem. But then I switched to u's and I left 0 and 2, right? So now 0 and 2, these are x values. Right? But all my variables in the problem are now u's. So I have not changed everything to u. So technically I have written a bunch of incorrect statements here, a bunch of untrue equations, because those are x values. And then in the next one it's really clear because at this point this says plug a 2 in for u, plug a 0 in for u, and see what you get, right? At this point, really what I should do is do 2 to the 4th, which is 16 over 8 is 2. Plug in a 0 and you get 0. It would be easy to say the answer is 2, right, which is wrong. 0 and 2 are x values. It doesn't work because 0 and 2 are x values, not u values. Okay, so that's the problem, is the 0 and the 2. They're x values, not u values. We knew that they were x values, which is why we substituted our x back in before we tried to plug them in. But this is like shady, right? There's some problems writing those equal signs. It's not actually equal. Okay. So if you want to do it correctly, we also have to change the limits of integration. Okay, so I'm going to start this again. My u is x squared plus 1, which means du dx is 2x, which means dx is du over 2x. And then u of 0, I'm going to change my limits of integration. What is u of 0? 1. You use your formula for u, right? We have a formula for u in terms of x. So when x is 0, u is 1. And when x is 2, what is u? 5. Yep, so 2 squared plus 1 gives you 5. Does that make sense? So now I start my whole problem again, and I change the limits of integration. And then I don't have to worry about ever going back to x's. It actually saves you a lot of time in the long run. So this becomes the integral. I'm changing to u's now, so I'm going to put a 1 and a 5 as my limits of integration instead of a 0 and a 2. And this becomes x times u cubed times du over 2x, the same u substitution we did before. The x's cancel. Pull the 1/2 out of the integral. So this becomes u cubed du. Take the antiderivative, and you get 1/2 times u to the 4th over 4, evaluated from 1 to 5. I could actually make this u to the 4th over 8, evaluated from 1 to 5. And when I plug in a 5, 5 to the 4th is 625. So I have 625 over 4 minus 1 over 8, and that comes out to 78. Sorry, that should be 625 over 8. There we go. Yep. Yeah. Yes. That's why you have to change the dx to a du, so you know what variable to focus on. Yeah. Good. So if you're doing a u substitution, you really need to change the limits of integration at the moment the variable changes from x to u. So method 1 does get you the right answer, but you've written a bunch of actually incorrect statements to get there. So you will lose a little bit of credit if you do it that way. Method 2 is the better method. What it says here down here at number 2, if you do a u substitution, you need to change the limits of integration the moment the variable changes from x to u. All right, so here's a fun integral we can do now that we know u substitution. So I asked you to memorize the integral of tangent x dx. Anybody remember what it is? Negative ln of cosine of x. Good. So at this point, now that we know u substitution, we have the ability to actually derive that. So right, you know what it is because I made you memorize it, but we can actually figure it out now. So this is the integral of tangent x dx. The trick here is to rewrite tangent as a quotient sine over cosine. So this becomes the integral of sine x over cosine x dx. All right, so sine and cosine are derivatives of each other, right? The derivative of sine is cosine, and the derivative of cosine is negative sine. So I could use u substitution as a good prospect here, because we have functions in the integrand whose derivatives also show up in the integrand. All right, so you might guess sine x will work, but then that one won't. So let's try u equals cosine x. So where should I write my side work? I'll write it up here. If we let u be cosine x, that means du dx is what? Negative sine x. And then I solve for dx. Just in this equation, treat du dx like a fraction, solve for dx, and I get du over negative sine x. And then I make my substitution. This is an indefinite integral. There are no limits of integration, so I don't have to worry about changing them since they don't exist. All right, so this becomes the integral. Sine x doesn't have a direct substitution up here, but cosine x becomes a u, and dx becomes du over negative sine x. And my sine x's cancel. So I have a negative sign now that got introduced into my integral. I can pull that -1 outside of the integral. And this becomes the integral of 1 over u du. What is the antiderivative of 1 over u? ln of u. It's actually the ln of the absolute value of u. Okay, so this, I've got a negative sign, and then I've got an ln, the absolute value of u, plus c. And then I need to substitute back in for my u. The u was actually cosine x. So this becomes negative ln of the cosine of x plus c. Explain what? Negative ln u plus c? It's just a rule that we know. The antiderivative of 1 over u is ln u. Right, because we know that the derivative of ln is 1 over u, so we just go backwards. Okay, so I've avoided talking about this absolute value piece of the antiderivative of 1 over u being the ln of the absolute value of u. We know that the derivative of the ln of u is 1 over u, right? So we know it in the reverse order. So why do these absolute value bars show up when we reverse it, when we take an antiderivative? So let's think about it for a little bit. So I know that the derivative of the ln of x is 1 over x, right? We learned that in Calc 1. Derivative of ln x is 1 over x. But this is actually only true for positive x's. Otherwise, the ln isn't even defined, right? The natural log function only exists for positive numbers. Okay, so this is only for x positive, right? So if I want to take an antiderivative of 1 over x, you get ln x, but only if x is positive. Okay. What if x is negative? What if x is negative, right? So maybe we're going to make a guess here. Maybe if we integrate 1 over x dx when x is negative, we know if it's positive, its integral is ln x because we can just reverse the derivative rule. But I'm going to guess that if x is negative, we get the ln of the opposite of x. Okay. Total guess. I just did that because if x is less than 0, then the opposite of x is positive, right? If x is already negative, if you put a negative sign in front, it becomes positive. And so now the ln is defined again, right? So the problem was that I couldn't just make it ln x because x is negative and then ln doesn't exist. So this is a wild guess right now. Is that true? Okay. So if that were true, I'm going to need more room here to explain this. If this is true, that means that we have to check, is the derivative of the ln of negative x, does it actually give me 1 over x back? Well, the derivative of the ln of some stuff is 1 over the stuff, and then times the derivative of the stuff. What's the derivative of negative x? Negative 1. My negatives cancel, and I just get 1 over x. So it turns out there are 2 functions whose derivative is 1 over x. ln x, the derivative of ln x is 1 over x. Already knew that one, right? But the derivative of ln x, the derivative of ln of negative x, also gives you 1 over x. Okay, so there are 2 functions whose derivative is 1 over x. So when I'm trying to take an antiderivative, I have to sort of combine them into one statement. So let's see. The integral of 1 over x dx. There are two functions that have that as its derivative. ln x or ln of the opposite of x, right? This one, when x is positive, right? Because ln x is only defined when x is positive. This one, if x is negative, because ln of opposite of x is only defined if x starts as negative. Okay. What function do you know is defined as x when x is positive and the opposite of x when x is negative? The absolute value of x, right? So I can write this as one statement, 1 over x dx. The integral of 1 over x dx is the ln of the absolute value of x. Yep. Okay, so yesterday I lied to you a little bit, or last class I lied to you a little bit. I said if all the x's don't cancel, then you either chose a bad u or u substitution is not a good method, right? That's not always true. Okay. Sometimes all your x's won't cancel, and you just have to do something a little tricky. Okay. These can be hard to recognize, but just before you give up, be like, should I try a little trick, right, before you give up? All right, so this one is a really tricky u substitution. Okay, so I've got the integral of x squared times the square root of x minus 1. Now I'm torn on what to choose for a u, right? Because typically we like to choose u's that are embedded in a composite function, the inside of a composite function, which would suggest x minus 1, because it's under the square root. But I also like to choose functions whose derivative also shows up in the integrand, which would suggest x squared, right? Because its derivative is x and there's an x in my integrand. There's no way that you would know which one would work ahead of time. You have to just pick one and try it. I'm going to pick the one that works because I tried both earlier. Okay? So I'm going to tell you that we're going to choose u to be x minus 1, the inside function, just to save us the time of doing one that doesn't work. Okay. All right, so that means du dx is 1, which means du equals dx. So then we go back to our integral, make all our substitutions. So I have the integral, x squared doesn't have a direct substitution, and then this becomes the square root of u, which is the same thing as u to the 1/2, and dx becomes du. At this point, last time we spoke, I said, if all your x's don't cancel, you chose a bad u, or this is just a not an appropriate method for this integral. Okay, so at this point, you might erase it and try the other u. Try x squared as your u, right? Or you can try and be a little tricky. Go back to your equation where you defined u. U equals x minus 1. What does x equal if you just manipulate that equation a little bit? U plus 1. So now I could replace anything that still has an x in it with a u plus 1. So this becomes the integral of u plus 1 squared times u to the 1/2 du. Then I can simplify that integrand by squaring out the u plus 1, distributing the u to the 1/2, and it'll just become a simple power rule antiderivative. So this becomes u plus 1 squared is u squared plus 2u plus 1. Got it? Okay. All right, so all I did here was square my u plus 1. Now I'm going to distribute my u to the 1/2. Remember, multiplying like bases, you add the exponents. So this is going to become the integral of u to the 2.5 plus 2u to the 1.5 plus u to the 1/2 du. And then I can just use the power rule to integrate all of my terms. Right, so the power rule says just increase the exponent by 1 and then divide by the new exponent. So this becomes u to the 3.5 over 3.5 plus 2u to the 2.5 over 2.5 plus u to the 1.5 over 1.5 plus c. Then replace your u's with x minus 1s. X minus 1 to 3.5 over 3.5. So at first, it looked hopeless. At first, it looked like, oh, shoot, my x's didn't all cancel. But I was able to salvage the integral by substituting a new expression for x in terms of u. It won't always work, but it's something to try before you give up and try a new method.